Welcome to Learn Elite Academy. Today we are here to make a video on physics, on the term physical quantity. Physics term physical quantity. What is a physical quantity? A physical quantity are quantities that has a numerical value and physical properties. I come again. I said that physical quantities are quantities that has what? A numerical value and physical properties. But here we will be looking at the word, the classification of physical what? Quantities. When we are looking at the classification, like this physical quantity is classified into two. You understand? It's classified into two where we have what? Fundamental. We have fundamental quantity. We have what? Derived quantity. Derived quantity. Now, if you look at it, these are the classification of what? Physical quantities. Classified into two. Fundamental quantity and derived what? Quantities. But now, here, we want to look at them one after the other. First of all, we want to talk about fundamental quantity. Another word for fundamental quantity is basics. The basics. You understand? So, I cannot say that fundamental, like here now, I want to talk about fundamental quantities and units. Take note. Fundamental quantities and unit. We have to look at it. Fundamental quantities and unit. What is a fundamental quantity? A fundamental quantity are basic quantities that are independent of other quantity. So when we are talking about fundamental quantity does not depend. That is why we say that they are the basic quantity that are independent of other quantities. You understand? So now, when we look at it, fundamental quantities, we see how we call fundamental unit. But what you must know about the fundamental quantity is that they are independent of other quantities. Other quantity depends on them. That is why we say that they are the basic quantities. So every other quantities are gotten from these fundamental quantities. So that is for that. So when we now talk about fundamental units, they are simply the unit of the fundamental quantities. Fundamental units are the unit of the fundamental quantities. So you have to take note of that. So what are these fundamental quantities? What can we use to represent them? Look at me. For example, when we talk about fundamental quantity, first of all, example, I can talk about length. I can talk about mass. I can talk about time. I can talk about temperature. I can talk about electric current. I can talk about amount of a substance. I can talk about light / luminous. Noise intensity. I can talk about this. You see now? So, but what I want you to know now is that, like we talk about these are the quantities. We call them quantities. Quantities now. You understand? What about their unit? If I want to look about their unit, I can talk about their unit here. I will say units. For example, if we are talking about this length as a fundamental quantity, the unit of this is a fundamental unit. You see now, being that length is a fundamental quantity, the unit of length is a fundamental unit. And what is the unit of length? Unit of length is meter. And in symbols, we represent it as what? M. Look at it. Now, when we say length, the unit of length, that length is a quantity, is a fundamental quantity now. The fundamental unit is meter, represented as this. But now, when I come to mass is in kilogram. And the fundamental unit, as a fundamental unit, the symbol, we take it as kg. Time, we said is what? Second, which is what? S. Temperature, we take it as Kelvin, which is what? K. Electric current is ampere, A. Amount of a substance is mole, which is this. And luminous intensity stroke light intensity. The word luminous, light. Luminous. Bodies that have their own light. We are talking about light now. Intensity. That is to say, we say candela. Candela. CD. So all these are the fundamental word quantities, units, and symbols. But now, anything that is not here, it means it's not part of the fundamental quantities and units. Any quantity that is not here, any unit that is not here now in the entire physics is not part of what? Fundamental word quantities and what? Units. And when we are looking at this fundamental quantity like we have listed so far, in these fundamental quantities, there are three most important fundamental quantities in mechanics for physical world measurement. Three. There are three most important fundamental world quantities in mechanics for physical world measurement. What are they? We talk about length, mass, and what? Time. Length, mass, time. These are the three most important fundamental quantities in mechanics for physical world measurement, of which the internationally agreed system depends for physical measurement. Now, when we talk about the international agreed system of unit, listen carefully. When we talk about the international agreed system of unit, they depend on these three most important fundamental units. Fundamental quantity. So when we talk about the international agreed system of unit, depends on length, mass, time. And what are they? The international agreed system of units. What are they? We talk about what? We talk about kilogram. We talk about meter. We talk about second. These are the three most important fundamental what? Units. These are the three international agreed system of units for physical measurement. Now, like we have said, we just talked about fundamental quantities and whatever. But now listen. Here, I want to be talking about derived quantities and units. Derived quantities and units. Now, when we are talking about derived quantities, here, there are things I want us to look at. Are you getting it now? There are things I want us to look at here. Derived quantities. Derived quantities are those quantities gotten by dividing or multiplying two or more of the fundamental quantities. I said derived quantities are quantities gotten by dividing or multiplying two or more of the fundamental quantities. Derived quantities, they depend on the fundamental quantities for existence. Derived quantity, they depend on the fundamental quantities. Now, when we talk about derived quantity, we also have derived units, which are also the units of the derived quantities. And this unit, they also depend on the fundamental unit. Are you getting me now? And what example can I give as an example of what? Derived quantity. If I want to give an example here, when I talk about quantities, I can talk about definition. I can talk about units. I can talk about symbols. Look at them now. Now, if I want to look at quantities, derived quantity, for example, I can talk about I can talk about velocity. slash speed, I can talk about this. I can talk about velocity slash speed. Why I put it like this is because both has the same word, unit. And when we say velocity, we know that velocity is what? Displacement. Displacement. Slash speed is distance. Over what? Time. But now, when we are talking measuring displacement, distance, they are in meter. So I can meter divide by minute in meter per second. So here now I can say, since this one is meter, the up one is meter and the bottom is second, I can say it's meter per second. I can write meter per second. While the symbols, I can represent it as this. Sometimes, or people can write it like this. You can say write it like this. Depends. But number 2 here, I can look at acceleration. Acceleration. I can look at acceleration. What is acceleration? Acceleration is change in velocity divided by what? Time. And the unit, since this one is already in meter per second, and this one is in second, we can represent it as meter per second square. Meter per second square. That is when we are talking about what? Acceleration. Why here, if I talk about number 3, I can talk about area. I can talk about area. Area, we say that is what? Is length. Length times breadth. Length times breadth. Length is in meter, breadth is in meter, it becomes meter square. Meter square. So here if you say here meter per second square, this is how you write it, meter per second square or meter slash square. Why here now we have meter square? Meter square, we cannot say that the symbol, we write it as meter what? Square. Now we have again number 4. We talk about volume. What is it, volume? Volume is length times breadth times height, which is what? Meter times meter times meter become meter cube, which can be represented as what? Meter raised over 3 meter cube. Become like this. Now number what? Number 5. I can represent force. I can call force. Force. What is it when I say force? Force here, according to Newton's second law, we were meant to know that force is mass. Is mass times acceleration, which is defined as Newton. By unit, we call it Newton. By Newton. But I want to make you know that the original formula for force is not Newton. It's a honor to the Isaac Newton that stated the second law, the first, second law, third law, which is Newton's first law, second law, and it's a honor to him. So if we say Newton here, since we said that force is mass as acceleration, and we are using Newton, it simply means that Newton here can serve as, or we can say, or mass is kilogram. Acceleration is meter per second square because kilogram meter per second squared. So if it's either we now represent this or this, we cannot say either Newton or, look at it, kilogram meter per second square. We have it kilogram meter per second square. So meaning that Newton is equivalent to this. Like I said, I told you it's a honor. Take note. This Newton, the unit is in Newton. Force is in Newton. Why? Because the man that discovered, that stated the laws, first law, second law, and third law, this unit was used as a honor. So the original word, unit of force is this. So Newton is expressed as this. 6. We talk about work. I can talk about work. Or I can talk about work through energy. I can talk about energy. I can still talk about, that is all energy. Work, all energy. Take note. I can talk about torque. Or let me say, I can say, let's say work energy. Let me take it like this now. Work energy. Let's look at it. Because why work is measured in joule, energy is measured in joule. Even moment of a force, they have the same formula definition. Moment of a force, torque, which is coupled, they all have the same unit, the same dimension. That is why we always bring them together, because there are some questions that come like that. They will ask a question that which of the following have the same unit, the same dimension. Are you getting me? So because of that, you must know that when you talk about work, is force times distance. Energy, force times distance. Moment of a force times distance. Torque or couple, force times distance. Always know that they go together. So when I come here, I will now define it. I will say there is force times what? Distance. Which is force times distance is what? We say joule. Force times distance, let me put it well. Force times distance, force times distance. We take the unit as joule. The same thing that happened to Newton is the same thing that is happening here now. Joule is a name of a man. This is not the original unit. Are you getting me now? So the unit, the meaning of joule, we can say or Newton meter. Take note of that, because we say force times distance is Newton meter. Joule is a honor, so it means Newton meter because of the formula here. Force is in Newton, distance, so we take it Newton what? Meter. Or sometimes I can still come now, being that Newton is a honor, I can still take it as, or I will say kilogram. I can take it kilogram. Kilogram meter square per second square. I can take it like this. So when we use the word joule as the unit symbol, joule there signify what? Newton meter, or we say or Newton meter, which is, we can still say or kilogram meter square per second square. Look at it. That is what we signify. So joule means this. This is what joule stands for. This is what it stands for. Take note of that. Force times distance. Force is Newton meter. And we said that Newton, look at Newton here. We define this is Newton. So you place it there. Meter times this meter give you the meter square. That is it. Now, number 7. Let's look at power. What is the unit of power? What is power? What is the definition of power? Power is work done. Work done over what? Time. Taken. That is power. And power is in watts. Watt. It's measured in watt. Wattage. Wattage. Are you getting it? Which is the same. Wattage or work done is joule or joule per second. Take note. Work done divided by time. Work is in joule, time second. That is joule per second. Work done is in joule per second. Now, another thing again, listen, we talk about work done, joule per second. Now, I can come here now, I will say watt or joule per second. I can write it like this. Joule per second. And again, if I want to look at joule, full meaning of joule, we have discussed it in our previous listing. Joule per second. So in here now, if I want to look at it, I can still write and say or, look at me, I will say or kilogram. Kilogram meter square per second cube. You see? So I can say or kilogram meter square per second cube. I can look at it like this. That is the unit of what the word joule per second. This is what it stands for. Take note of that. In terms of the fundamental SI unit. You see now? Good. Now let's look at pressure, stress. Why I'm taking it like this is this. Because of exam condition, you might be asked, which of the following has the same unit as this? So I'm trying to tell you now that pressure and stress, they have the same formula. They have the same unit. They have the same dimension. Now, when we talk about pressure, stress, the one that have the same unit as this too, we still have energy density, have the same unit as pressure. Young modulus have the same unit as pressure. Are you getting me? So in case they ask you which of the following have the same dimension, the same unit, you must look at that. Look at me. So from here now, I'll say pressure, stress. What is it? Force over area. Force over area. What is it? Force is in Newton. Per what? Meter square. Per meter square. We have it like this. Force is Newton per meter square. Take note of that. Which is this? In symbol represented. So in case if you are asked, you can also express it now. You can express it yourself. Take note of that. Let's look at number 9. We now talk about gravitational constant. Let's look at it. Gravitational what? Constant. Gravitational what? Gravitational constant. Gravitational constant. Now, when we talk about gravitational constant, what is it? It's a force. Force times distance squared divided by what? Mass by mass squared. Meaning here, force is Newton. That is the unit now. Distance is meter squared. Distance squared. Meter squared. Newton meter squared. Newton. Now, you see now Newton meter squared per kilogram squared, which is given in symbols as Newton meter squared per kilogram squared. That's the unit of the gravitational word constant. Now here, we are now to look at the other part now. We want to talk about dimension of a physical word quantity. The dimension of a physical quantity. What is dimension? The dimension of a physical quantity is the physical nature of a physical quantity. I said the dimension of a physical quantity is the physical nature of a physical word quantity. What does it do? It helps. It indicates how it is made up. Are we there? in terms of the SI unit. The dimension of a physical quantity indicate how it is made up in terms of the SI unit. Now we talk about SI unit. What is really a unit? What does it stand for? A unit is the standard that we choose to quantify a dimension as a physical nature of a word, a quantity. A unit is the standard that we choose to quantify a dimension as a physical nature of a quantity. Now, how do we obtain the dimension of a physical quantity? Now, what I want you to know now is that to obtain the dimension of a derived physical quantity, first, we express the unit in terms of the fundamental unit. For example, when we talk about fundamental unit, what are the dimensions of the fundamental unit? Let's look at them on the board. Let's look at them. Now, when we talk about dimension, let's talk about quantities. Quantities. We talk about units. Units. We talk about symbols. Okay, sorry, dimension. Dimension. For example, I can talk about mass. When I talk about mass, we know that mass is in kilogram, kg. Mass is in kilogram. What is the dimension of mass? What do we mean by this kilogram? What is the dimension? We represent it with m. That is the dimension. Now, when we talk about length, we know it's in meter. And the dimension, we use L, capital letter. When we talk about time, we talk about what? S, second. And here we use what? T. And here when we talk about temperature, when we talk about temperature, now we talk about temperature. Temperature, we said, is in Kelvin. And what is the dimension? We use theta. We talk about electric current. Electric current. We use ampere as a symbol. And we use this symbol here, R, capital letter, R. We talk about amount of a substance. Amount of a substance. What is it? We use mole. This dimension is n. We use small n. What about light? Stroke luminous. Intensity. We use CD, but no dimension. So when we talk about dimension, whenever you come across kg, you use M, capital letter. When you come across what? M, you use L. When you talk about S, which is second, use T, capital letter. When you talk about Kelvin, K, use theta. When we talk about ampere, we use R. We talk about mole, we use N. We talk about CD, no dimension. Now, if you look at the board, we have some examples here. The example here says find the dimension of the following physical quantities. For example, we have velocity. Velocity is a derived physical quantity. Acceleration, force, work, pressure, gravitational constant, electromotive force. You are given a question like this to solve. How do we start? How do we start with this? First of all, for one to know the dimension of a physical quantity, you have to first of all know the unit of that physical quantity. Are you getting now? We have to know the unit of that physical what? Quantity. After you have gotten the unit, then you can from the unit get the dimension. Now let's look at this. For example, now we have velocity. We have velocity. Without stressing yourself, we know that solution. One, now we have velocity. We know that we said that velocity is displacement over time. What is the SI unit of velocity? If displacement is in meter, time is in second. That is to say, we can say that is meter per second. So we say meter per second. We write it like this. This is meter per second. So this meter per second now, if I want to write the dimension of this now, I cannot say dimensionally, I can write the meter per second now. What is the dimension of meter? Meter, displacement, what is meter? From the fundamental quantity, meter, length is measured in meter. The unit of length is in meter. And the dimension of this length, meter, which is L. In place of this now, I will write L. Then you come to second. Second, what is it? Time. What is the dimension of time? Dimension of time here is T. You can now write it T raised to power minus what? 1. Automatically, this becomes the dimension of what? Velocity. Now, number 2, we have acceleration. Acceleration. What is it? Change in velocity. Change in velocity over what? Time. Change in velocity over time. What is the SI unit of acceleration? We said it's meter per second square. The SI unit, because if you change the velocity, velocity is meter per second square. Divide by what? Time again, it becomes meter per second square. So which is this? Velocity is meter per second. Divide by what? Second, it becomes meter per second square. So in other words, we cannot say what is the dimension now of what is the dimension of acceleration now? Since the unit is in meter per second square, we come back to the fundamental what? Table now. These are fundamental units. All these are fundamental units. So let's look at it now. When coming back here, meter, this is meter, length is in meter. The dimension is L. We take it as L. S is second. Time, dimension of what? Second, which is time, is T. Look at it. You write it T raised to power minus 2. This is the dimension of what? Acceleration. Now here we talk about number 3 now. Here now, when we come to number 3, we are talking about number 3. We talk about force. We talk about force. What is the dimension of force? So if we want to look at force, first of all, force, we already know the unit as what? Newton. We know the unit as what? Newton. This is the unit of force. And according to Newton's second law, what is force? Force, we said, is what? Mass times what? Acceleration. So we mean that acceleration is mass times force is mass times what? Acceleration. So if I say that the unit of force is Newton, it means that Newton, what is it? Look at me. Unit of force is Newton, and force is mass times acceleration. What is mass here? Mass here is kilogram. That is for this mass. What about acceleration? Meter per second square. I will not say times meter per second square. Therefore, Newton is now equivalent to distances become kilogram meter per second square. How do we now say what is now the dimension now? According, we have just expressed Newton in terms of the fundamental SI unit now. So what does kilogram stand for? What is kilogram? What is the dimensional statement of what? Kilogram. The dimensional statement of kilogram we said is M according to the table. Look at it. Kilogram, M. Meter, length, we take it as L. Second, T, we take it T raised to power minus 2. This becomes the dimension of force. Now, we want to look at the other one, number 4, work. What is it, work? What do we say, work? Work. We said it's what? Work is force times distance. Work is force times distance. And when we say force,
is a honor. Force is measured in joule. Force is measured in what? In joule. So let's define joule. It means that if work is force times distance and joule is the unit of force of work, then we say joule now, force will now become Newton. Times what? Meter. You see now? So now, what is it again? As we progress, let's look at it. Like I said, we now say that joule now is Newton meter. And again, if we say so, by saying what is force, this force, we said it's mass times acceleration times distance. Because if force is mass times acceleration times distance, we cannot say that this become what? Mass is kilogram. Acceleration times meter per second square times meter. Finally, we say that kilogram, which is this, meter times meter become meter square per second square. So originally, we cannot say that the dimension kilogram is m. From the table, look at it, kilogram, m. Meter is L. So we come here now, we say L raised to power 2. S is T raised to power minus 2. So this is the dimension of what? Work. S is T, look at it here. S is T, M is L, kg is M, look at it. Kg is M, M, which is meter, is L square, S, T raised to power minus 2. This is the dimension of what? Work. Now, number 5 here, we have pressure. Pressure. What is it? We said that pressure is force over area. Force over area. Pressure, force over area. Meaning is what? The unit is Newton per meter square. Look at it. Newton per meter square. Look at it. Area is meter square. Force is Newton. So now as we go on, force is what? Mass times what? Acceleration. Here, area, length times what? Breadth. So in other words, if I come back here, we say that here now, the unit here, we have it as what? Kilogram. M, kilogram. Take note, kilogram. Acceleration is meter per second square. Divided by what? Here now is what? Meter times what? Meter. Now, meter can cancel meter. At the end of the day, we are going to say that kilogram. This meter, when it comes up, it becomes raised to power minus 1 per second square. From indices, observe this. When you have anything A, 1 over A raised to power S, anything in this nature, you write it as A raised to power minus S. When you have 1 over A, it means A raised to power minus 1. So here now, if you have here now, remember, here now is 1 over M. 1 over M is here. So that over M, as this one is coming up, it becomes this. So we cannot say that the dimension, kilogram in dimension according to the table, we represent it as M. L according to the table represents meter. T represents what? Second. So we take this as the dimension of what? Pressure. It's also the dimension of what? Energy density. The same thing, we can still take it as a dimension of what? Energy density. We can talk about stress. It's still the same thing. Young modulo, this is the same thing as their dimension. Oh, they are the same thing. Take note of that. Now, here we want to look at gravitational constant. Now, if you are looking at gravitational constant, listen carefully. A question can come like this. Say calculate now, find the dimension of this. Gravitational constant. Remember, according to Newton's law of universal gravitation, it was stated that the force of attraction varies directly as the product of the mass of the particle, m1, m2, and inversely proportional to the square of their distance apart. We now say that therefore, that F become what? G, m1, m2 over r square. We have it like this. This for the gravitational world. Now G they serve as the gravitational constant. So if we make G the Sawyer formula, we are going to say therefore G can have be what? F arrow square over what? M1 M2. From here now we want to get the unit now. The unit of this gravitational what? Constant. We have it, we take the unit now. The unit force is in Newton. Arrow square, meter square. Arrow is a distance, meter square. Mass, kilogram square. It become per kilogram square. Kilogram square there. It become like this. This become the unit of the gravitational what? Constant. So how do we go with this? Now let's try to break down force. Newton now. Newton here is the unit of force. So if I come back here now, I cannot break down force now from here now. Let's look at force here. From the gravitational constant, I can say gravitational constant now. I can say force is mass times acceleration times arrow square divided by mass times mass. So one mass can cancel this mass. So at the end of the day, I cannot say, to break this down now, I cannot say acceleration now. Look at one mass now. It become, when this m come up, is mass. The unit here now, I cannot say is meter per second square times meter square over per kilogram, because mass is in kilogram. So generally, I can write and I will say that here now is meter. Meter times meter. This is meter cube. Take note of that. Because here we have here arrow square. So here we have meter cube. So here kilogram, when it comes, it becomes per kilogram raised to power minus 1. Meter what? Cube per second square. It becomes like this. So in this case now, what have we done? We have succeeded in expressing this in terms of the fundamental unit. Fundamental unit, kilogram, meter, second, they are fundamental what? Unit. So in other words, I cannot say kilogram there is m raised to power minus 1. Meter is length raised to power 3. Second is t raised to power what? 2. This is it. The dimension of what? The gravitational what? Constant. Now here we want to look at electromotive force. And what is it? Electromotive force is the PD across a cell. Is the total PD across a cell when the cell is not generating what? Current, not supplying current to an external resistor. So the total PD across a cell is what we call this. So in other words, we can still say that is the work done when a unit charge move from one point to another in an electric field. So now I can say that electromotive force here now, I can denote it as V. I can say that it's the same as the work done over what? Charge. We can take it like this. Work done over what? Charge. So if I take it as this, what is work done? We say that work done here is force times what? Distance. The work done. Why here charge? We take it as charge. Charge is I what? IT. Charge is IT. Now force times what? Distance. Charge is IT. So in other words, I can say force, we say is mass times acceleration times distance over what? I times what? T. So meaning that the unit here, you know that the unit of this, we say is volt. It's voltage. The unit is in volt. Since it's in volt, what is volt? Volt is joule per coulomb. You know, work done over charge. Work is in joule. Divide by what? Charge, coulomb. Joule per coulomb. Which is the same. Here now we have it as Newton times distance, Newton meter. And here remember I is ampere. Ampere per ampere per second. I here is ampere, the unit. Current is ampere per ampere when it comes up, because raised to power minus 1. T is second per second. Look at it. Which can now officially, to define this Newton, mass as acceleration, which is kilogram. Kilogram. Meter per second square times meter divided by what? Ampere, which is ampere times what? Second. Generally, we cannot say that this become what? Kilogram. Look at it. Meter square. Meter times meter. When this second here, when it go up, it become what? Yes, per ampere. Per second cube. Because this one go up, it become per second cube. So the dimension here cannot be what? Kilogram is m. L square. Ampere dimension is what? Called R. T raised to power minus 3. This becomes the dimension of electromotive force. Now, from here now, we can see look at resistance. From Ohm's law, we were made to know that resistance is voltage over what? Current. And we just defined voltage just now. Remember when we were talking about voltage, we said that voltage on its own, we said that voltage is what? Work done over what? Charge. Is what we said. So in other words, if I come here, it will not be what? Work done over what? Current times what? Charge. It becomes like this. So in other words, I cannot say force times distance. Yes, current. Charge is current times time. Charge, IT. Force is mass times acceleration times distance divided by what? Current square times T. So at the end of the day, if I want to look at resistance, we say resistance is in ohms. Look at the symbol for resistance. The unit of resistance, ohms. What does it mean? What is the meaning of ohm? Ohm means volts. Volts per ampere. Let me use it, volt per ampere. Volt per ampere. That is the meaning of what? Ohms. Volt per ampere. You see it now? Here now we can say that is joule. You see now, work done, joule. Per ampere per coulomb. Look at it. Joule, this is joule. Per ampere per coulomb. Look at it. Joule per ampere. Current is ampere per coulomb. Look at it. We go further now. We have it again as Newton. Look at it. Yes, Newton. Newton. Meter. Ampere times ampere. Current. Ampere times ampere become ampere square. You see now, when they go up now, here now becomes per second word square. So finally, what is now Newton? Here now Newton, we said is mass. Look at it. Kilogram. Mass is kilogram. Mass times acceleration is meter per second square. Times meter. Divide ampere square times what? Second. So generally I will say kilogram. Look at me. Meter times meter. It becomes meter square. We have meter times meter square. This second, ampere per ampere square per second raised to power 3 cube per cube. So dimension now, kilogram is m. Length is square. Ampere is r. T raised to power 3. This is resistance. Resistance. Now, example 2 here. The dimension of Young modulus is written as this. Determine the value of S, Y, and Z respectively. Now, in a case like this, first of all, like I said, when we say Young modulus is an elastic constant. It's an elastic what? Constant. It's the ratio of stress to strain. That is Young modulus. Remember when I was talking that I make use of pressure, I say I have the same unit as pressure, and you are going to see it from here. We said that pressure is in Newton per meter square, but let's check if it's true. They have the same unit and the same dimension. Now, all I want you to know now is this. In this case, I want a picture here. Look at the picture. We said that stress, Young modulus now, what is stress? Stress is force over area. And here we have strain. Strain is what? Extension over original length. That is it. Are you there? Stress there is the ratio of the force per unit what? Area. While strain is the ratio of the extension produced to the original length of the what? The elastic material. So in other words, here now if you look very well, extension is in meter, length is in meter. In other words, so the unit here, the stress has no unit. Since stress has no unit, we now say that the unit here now, please take note now, we want to talk about unit here, we say here is Newton. Listen, oh, here now we say that here now is what? Force is Newton. Look at it. Force here is Newton. Area become per meter square. Here now let's divide over. Here is meter over meter, which is 1. So strain has no unit. You see now is 1. Extension is in meter. Original length is in meter. Meter cancel meter become 1. So meaning that this is the unit of pressure the other time. Look at it, the same thing here. So when we talk about Young modulus, the unit of Young modulus is Newton per meter square. You see now? So in other words, what is the unit now? We can go on now. What is Newton? Newton is the unit of force. Force is mass times acceleration. And we know that mass times acceleration, mass is a kilogram. Acceleration is a meter per second square. That is for Newton now. Newton is the unit of force. Force is mass times acceleration. Mass, kilogram. Acceleration is this. Times per meter square. Remember here is raised to power 1. So in other words, according to indices, we have kilogram, meter, 1 minus, we have 1 minus 2 per second square, which is kilogram. Here become minus 1 per second square. So the dimension here can be m. Kilogram is m. Meter is L raised to power minus 1. And here T raised to power minus 2. And if this is equivalent to this, look at me. If it's equivalent to this, I will write it like this. I will write here MS LY TZ. Now this is equivalent to this now. But remember that our S here is M. If this M is raised to power 1, S is 1. Look at it. Our S here represents this one. S is equal to 1. Y is equal to what? Minus 1. Z is minus 2. Z is minus 2. So the question is, it says determine the value of S and Y. S, Y, and Z respectively. Now, S is equal to 1, Y is equal to minus 1, Z is this, according to what is here now. Now, question B here, we say, at what respective value of S, Y, and Z would the unit of force, the Newton, be dimensionally equivalent to this? Now, let's look at it. Now, when we are talking about Newton, we say force. We said it's mass times what? Acceleration. Force is in Newton. We already know that before now. Mass is kilogram times meter per second square. So in other words, we have it as what? Kilogram meter per second square. So the dimension here, kilogram is M, and here we have L, M, meter, and here we have S raised to power minus, which is what? T raised to power minus what? 2. So if we equate this to M, S, L, Y, T, Z, we cannot say that M here is 1. So our S, look at it. S is 1, Y is 1, Z is minus 2. Look at it. S here stands as 1. M raised to power 1. M raised to power S is 1. L raised to power Y. L is raised to power 1 here. Y is 1. T raised to power minus 2. T, Z. Z is raised equal to minus 2, which is this. Now, so by this now we have come to the end of what? Fundamental physical quantity dimensions. So in our next class, we'll be talking about what? Measurement. The measurement of physical what? Quantity. Are you getting now? We are going to be talking about that. So what I want you to do, you click the button, you don't know what to do. Subscribe. That is just all.
we need from you. Enjoy yourself. Thank you.